Thank you for the introduction. So this is a joint work with Matt Weinberg, and we are both from Princeton University. Um, so, so auctions, they are everywhere in the internet economy. Traditionally, we would see auctions in auction houses when users are trying to buy items. But nowadays, you also have that ad auctions are a big part of ad revenue is a big part of the economy in many tech companies. But also in the government, many local and federal governments, they are also required to acquire goods through procurement auctions, and particularly spectrum auctions have received a lot of attention from the mechanism design community because of their complexity and constraints. But in this talk, I'll be focusing on this setting where we have a single item for sale. And we're going to assume there is any bidders and they have independent private values and they are drawn from some distribution D. In this talk, we're going to assume all bidders have the same distribution, but that doesn't need to be the case in general. But for simplicity, let's assume that the distributions are the same for every bidder. And bidders also have a quasi-linear utility, so their value is V minus P. And in this setting, we know from this breakthrough work from Meyerson in 81 that the optimal auction, he completely characterized the optimal auction, and in this setting is simply a second price auction with reserves, and that's guaranteed to maximize revenue. But the traditional assumption in mechanism design is this idea that the auctioneer has this commitment power where the auctioneer can commit to an auction format. And then we are thinking like how we can actually design mechanisms that are truthful under this assumption that the auctioneer can commit to implement this auction that he's promising. So what that means in practice is that we have Alice and she's willing to bid on this Meyerson auction. If she's willing to bid $80, then she's gonna bid her maximum value, and then say like a second bidder comes and bids $79, and then Alice is only required to pay $79 in the end. But for the point of view of Alice, it just sounds very suspicious that after she reviews her bid, someone comes and just bid below her. So in the end, she's almost paying her whole value for the item, and she's not really sure in an internet setting. It's not clear for Alice if Bob is actually a real bidder interested in the item. So happens that this actually happens in practice where we have seen many instances where in the internet world, the auctioneer doesn't have really the incentive to implement the auction that he's promising to implement. And because this economy is decentralized, it's very hard to enforce this power of commitment on the auctioneer. And there's many instances in practice where that doesn't hold, and the auctioneer has this incentive to create fake bids or like misrepresent on what's happening in the auction to improve his revenue. Well, we can ask, okay, can we implement these auctions in a different way? So easy way we can do that we know very well is the first price auction, where we just gonna sell the item to the highest bidder and then he's gonna pay his bid. So if Alice is bidding $80, she knows that if she wins, she has to pay $80. At this point, there is nothing the auctioneer can do to cheat and misrepresent what Alice has to pay for the item. However, this auction is not truthful. So if Bob comes and bids $10, Alice still has to pay $80. So in some sense, we are simply shifting the complexity from the auctioneer to the bidders, and now the bidders, they have to optimize their bidding strategy to try to minimize how much they pay for the item. Even though you get this property where the auctioneer cannot cheat on this auction without clearly revealing that he's cheating on the auction. So one question that we ask here is, okay, can we design auctions that are strategy proof for bidders, but also strategy proof for the auctioneer? Where the strategy proof for the auctioneer, we're going to define as credibility later on, but for now, just think in mind that when we say credibility, is some notion of strategy proofness for the auctioneer, where the auctioneer doesn't have an incentive to cheat for the bidder. Okay, so in this setting, we actually know that there is an auction that satisfies this property of credibility and strategy proveness, and that's the ascending price auction with reserves, which is a simpler equivalent implementation of the second price auction, where we're going to divide this auction in potentially unbounded rounds. In each round, the auctioneer is going to go and ask each bidder if they want to raise their bids in the item. And when there is no one else, when there's only one bidder in the auction, then the item is going to be allocated to that bidder, and he's going to simply pay the second highest bid. And beautiful work by Akabarpur and Lee in EC 2018, which was actually the best paper in that year. And recently they published in Econometrica this year. They show that the ascending price auction with reserves is credible when the reserve price is optimal. So they show a relation between being credible and optimal for the ascending price auction. But they show the impossibility result in the sense that the ascending price auction is the only auction that would have satisfied this property of being revenue optimal, strategy proven, credible. But as I described before, this auction has unbounded rounds of communication in the worst case. So it requires the auctioneer to go and communicate with each bidder, and potentially that can take a very long time, and that's very unpractical for many online applications. So one question we can ask here, can we actually introduce additional assumptions on these auctions to circumvent this impossibility result that they propose here? And happens, this is actually our main result, and we show that under mild cryptographic assumptions, it's actually possible to design a revenue optimal auction, strategy proof, and credible, and it only requires 2 rounds of communication. So we go from this setting where the only truthful and credible optimal auction would require unbounded rounds, but we can actually have this auction implemented with 2 rounds with these cryptographic assumptions. However, we have one caveat that this auction is not credible for every distribution. So in some sense, the cryptographic assumption is not a magic bullet that simply can solve this problem. And we really require to analyze the incentives for the auctioneer to tip on this auction. And that's the main contribution here. And the cryptographic is just a technique to actually help us to circumvent this impossibility. So let's define our communication model that we are going to be thinking for this auction. So as I said, there's any bidders, and we're going to assume that the auctioneer can communicate privately with each bidder. In some sense, that means that one bidder cannot observe what the auctioneer is talking with other bidders. And we're also going to assume that bidders cannot communicate. So in general, we are worried about collusion. So we don't allow bidders to communicate on these auctions. And we're also going to assume that there is voluntary participation, in the sense that a bidder cannot be forced to participate, and the bidder can leave the auction at any point in time. And we are also going to give even more power for the auctioneer and assume that the auctioneer is the only agent that know how many bidders there are in the auction. So if it is in the best interest for the auctioneer to create fake bidders, we're going to allow that to happen, because the auctioneer is the only person that actually knows how many bidders there is on this auction. So let's define what credibility is. So the first concept is related to this notion of safe deviation. So in their paper, Akabarpur and Lee define, you first consider deciding where the auctioneer is going to publicly promise to implement some auction format. And then we say that a deviation of this promise auction is safe if for all bidders, the outcome of the auction is consistent with some realization of this auction. So what do I mean by that? So imagine we have a second price auction where Alice bids $80 and the second bidder bids 50, and then the auctioneer in the second price auction, the auctioneer asks the Alice to pay for 79. So that's a safe deviation because that's consistent with the second highest bidder bidding $79. And because Alice can't observe the communication of other bidders, that just sounds like a possible outcome of the auction. So, and we define credibility, an auction as credible if there is no safe deviation from the auction that from the promised auction that would give more revenue for the auctioneer. So for example, if you have a first price auction, if Alice is the highest bidder and she's bidding $80, the auctioneer can only charge Alice for $80 because in a first price auction, my payment is only a function of my bid. And if the auctioneer doesn't give the item to the highest bidder, then he's gonna strictly get less revenue. So the first price auction is credible under this definition. So let's define our auction. It's called the deferred revelation auction. And our main ingredient is gonna be cryptographic commitments. So we assume there is a function commitment where Alice can commit to her value by using some random string, and he's gonna send this commitment to the auctioneer. And this has a property of being perfectly hiding in the sense that it doesn't reveal anything about her value to the auctioneer. And it has this property of being perfectly binding. Later on, Alice can convince the auctioneer that she had committed to V because it's infeasible for any bidder to find a different value that would map to the same commitment. Let's see how we can actually use this to implement a credible auction. So the first step is that we're gonna simply require bidders to commit to their bid. If Bob is a fake bidder, he's gonna send a fake bid without knowing the value of Alice. So he can say he can actually send a commitment bigger than her value. And then the auctioneer is gonna broadcast all the bids. And after this point, Alice is not gonna accept any more bids from the auctioneer. And then the bidders are gonna simply review their bids. So Alice review 80 and then Bob reviews 90. So in this case, the auctioneer actually doesn't give the item to anyone, and he loses the opportunity of charging Alice for the reserve price because he sent a bid that was higher than Alice. And then we're gonna simply implement the Meyerson. In general, we'd simply implement the Meyerson auction after revealing the bids. So in this case, the auctioneer actually doesn't make a profit by submitting a fake bid. But we might ask, okay, this is actually credible. So it's not hard to see that this auction is not credible. So the idea here is that there is really no cost for the auctioneer to submit fake bids. So in practice, the auctioneer could submit 100 fake bids. And then we simply observe that there also no cost for the auctioneer for aborting a fake bidder. So the auctioneer can now claim, once that he learns Alice is bidding $80, he can review every bid that was below 80 and hide every bid that was above 80. And for Alice, that sounds consistent. The auctioneers claim that those bidders left the auction, and by the model, we are saying that no bidder can be forced to participate. So it's definitely a safe deviation for the auctioneer to claim that those bidders left the auction before opening their commitment. And the auctioneer is simply claiming, oh, I just can't open those commitments because those bidders left the auction. So our solution to this problem is gonna be very simple. So what we're gonna do is we are gonna penalize any bidder for aborting the auction. So if any bidder leaves the auction, then we are gonna they're gonna be required to pay a penalty equals to their to this function f, which is a function of the number of bidders and the distribution, and the penalty is gonna be paid to the winner of the auction. And that's important because we can't trust the auctioneer to get this penalty, so it's gonna go to the winner of the auction. So in this example, suppose there's a single bidder from this uniform distribution on 0 and 100 with a penalty of 100. If you have the same example that we had before, then notice that the auctioneer is not gonna have any incentive to ever hide a fake bid because he can get a payment of at most 100. But if you hide any fake bid, then he's gonna get a strictly negative revenue in this case. So at least in this example, looks like the auctioneer doesn't have any incentive to hide fake bids. So our next question should be, okay, how big should be these penalties for the for this auction to become credible. So we have this intuition that if the penalties are higher, then the auctioneer would pay a lot every time that he has to hide a fake bid. And our first result is this for this class of distributions called MHR, which includes the uniform distribution that we had in the example before, is that when the penalties are at least Meyerson reserve price, then this auction becomes credible. And notice that the Meyerson reserve doesn't depend on the number of bidders. So in some sense, the penalties don't depend on how many bidders there is in the auction. But we can ask, okay, what happens for a bigger class of distribution? There is this class called regular distribution. And for this class, actually cannot get credibility. By that, I mean that there is a distribution where the optimal auction has revenue 1, and no matter what we do, for every penalty function, the auctioneer can extract infinite revenue from this auction, even when there is a single bidder from this distribution. So let's see why that happens for these regular distributions. So our example is we're going to assume that there is a single bidder from this distribution called equal revenue. And notice that for any price, the auctioneer can get a revenue of 1. And that is actually the optimal revenue the auctioneer can have on this auction. And let's define K to be the penalty that the auctioneer would have if there is 3 bidders in the auction and it has to hide a fake bid. The auctioneer is going to introduce 2 fake bids, one of 2K and the other of 4K. And when Alice bids less than the lowest fake bid, the auctioneer is going to review every bid. In this case, the auctioneer doesn't get any revenue from Alice because the Alice knows she's not the winner of the item. When Alice bids between 2K and 4K, the auctioneer is going to hide only the highest fake bid. And in this case, the auctioneer is going to get a payment of 2K, which is the second highest bid in the view of Alice. But notice that the revenue is strictly bigger than 0. In the last case, when Alice bids higher than everyone, then the auctioneer is going to review everything and is not going to pay for any penalty. And notice now that the revenue is strictly bigger than 1. So Meyerson revenue would be 1, and we're strictly showing that the auctioneer can easily get more 1 unit of revenue. So we show that this is not credible for this distribution. So in this work, we also show extensions. So we show that for MHR, we can get credibility. For regular, we cannot get anything. For this class called alpha strongly regular, we can actually get credibility when there is a single item, or when there is a single bidder in the auction. But when there is many bidders, we can only approximate. And there is a counterexample where the auctioneer cannot, where the absolute is necessary. The auctioneer can always get strictly more than Meyerson revenue. But we can make it as close as possible to the Meyerson revenue. So to conclude, so before this work, we knew that the unique, truthful, and credible optimal auction would require unbounded rounds, and that was the ascending price auction by the work of Akabar-Prue and Lee in EC 2018 and Econometrica this year. And now we know that under some cryptographic assumptions, we can actually construct credible and truthful auctions for MHR distributions and some extensions for alpha strongly regular distributions. And there's some interesting open questions like, can we actually construct credible auctions for regular distributions, or when in 2 rounds, or how about like if you have a finite K rounds on this auction? So thank you very much. Thank you for listening.